that is 1.26 meter. Okay, let's do another one. A steel wire having a mass of 5 gram and a length of 1.4 meter is fixed at both ends and has a tension of 968 Newton. Find the speed of transverse waves on the wire. Find the wavelength and frequency of the fundamental. Find the frequencies of the second and third harmonic. Well, this is old story. We have been doing problems like this. Find the speed of transverse waves on a string. What's the equation for speed of transverse waves on a stretched string? V equal to square root T over mu. Let's pick out data. Mass of the string is 0.005 kilogram, 5 gram. Length of the string is 1.4 meter. You have the length, you have the mass, you can find the mass per unit length. Is that right? Yes. The tension on the string is 968 Newton. Mass per unit length is mass of the string divided by its length. That is 0.005 kilogram divided by 1.4 meter. That is 0.0036 kilogram per meter. You now have the linear density mu, you have the tension T, we can find the speed of the wave on the string. V equal to square root of T over mu, and using the values of T and mu, we get V equal to 519 meter per second. Can you stay at this point and answer this for me? Find the wavelength and frequency of the fundamental. The fundamental. The wavelength of the fundamental is related to the length of the string. Is that right? The length of the string is equal to half of the wavelength. So if 1.4 meter is half of the wavelength, then the wavelength will be twice that. Alright, let's write down that. The wavelength of the fundamental is 2 times the length of the string. You see, this is the fundamental, the wavelength will be 2 times the fundamental and the 2 times the length. Therefore, that will be 2 times 1.4 meter is 2.8 meter is the wavelength of that wave. What is the frequency of the fundamental? Frequency of the fundamental is V over lambda. V we calculated. What was the velocity we calculated? 519 meter per second. Wavelength is 2.8 meter. Therefore, the fundamental frequency is 185.35 Hertz. Alright? Once you know the fundamental, do you know the second and third harmonic? The second harmonic is 2 times the fundamental. The third harmonic is 3 times the fundamental. So F2 equal to 2 F1, which is 370.7 Hertz. F2 equal to 3 F1, which is 556 Hertz. Alright, now these kind of problems are pretty good and you must be feeling pretty comfortable doing them. Let's do one more problem before we close this lesson. The length of the B string on a certain guitar is 60 centimeter. You know that a guitar has several wires, thin wire, thick wires, and each wire you can finger it to produce different frequencies, the do, re, mi, A, B, C, and so on. Here the B string on a certain guitar wire is 60 centimeter long and its fundamental is 247 Hertz. What is the speed of transverse waves on this string? if the linear mass density of the guitar string is 0.01 gram per centimeter, what should be the tension when it is in tune? What is the meaning that a guitar wire is in tune? A guitar wire is in tune means the string that is meant to produce a certain frequency, if it doesn't produce that frequency, then the guitar is out of tune. It is useless. You see? Because a wire that is supposed to produce the frequency B, that is 247 Hertz, must produce that frequency. And what are the factors on which that depends on? The tension of the wire. So the guitar is actually tuned by tightening the wire or loosening the wire, by increasing the tension. I'm sure you have seen people doing that. They pluck the wire and they turn the screw until the frequency is the right frequency. Well, let me see if I can show you a stretched wire and how the frequency depends on the length. Well, here I have a stretched wire. It is stretched between this point and this point. And I can adjust the tension by either pulling it backward or forward. Well, this is actually pushed to the limit. Now, listen to the fundamental note when I pluck it. I can actually see it doesn't record very well, but you can see when I pluck the wire, it vibrates in one segment. Can you see it? There you are. It's vibrating in its fundamental mode, producing that frequency. This is the fundamental frequency. Now, listen, if you can, what happens when I decrease the length. If I hold this aluminum rod here, I'm decreasing the length of the vibrating string. What happens now? What is the difference in the frequency? The frequency is now higher. If I decrease it further by bringing the aluminum rod, you can see the length is now decreased. You see? It is a higher frequency. If I increase the length, the frequency decreases. There you are. So, as you increase the length of the wire, its fundamental frequency decreases, and you decrease its length, the fundamental frequency will increase. All right. Okay, what are the given information in this problem? You are given the length of the wire, that is 0.6 meter. You are given the fundamental frequency, 247 Hertz. You are given the linear density. And now, what's the unit? It is given in gram per centimeter, 0.01 gram per centimeter. Convert that to kilogram per meter. That will be 0.001 kilogram per meter. Alright, what do we need to find first? What is the speed of transverse waves on the string? Well, to find the speed, what are the things that we need? Well, we can find the wavelength of the fundamental. Is that right? Now, how do we find the wavelength of the fundamental? Wavelength of the fundamental is related to the length of the string. You know that when a string vibrates in its fundamental mode, there are two nodes at the two fixed ends. The distance between two successive nodes is half a wavelength. So lambda 1, the wavelength of the fundamental, is 2 times the length of the wire, which is therefore 1.2 meter. The wavelength of the fundamental is 1.2 meter. The frequency of the fundamental is 247 Hertz. Alright, do we have enough information to find the wave speed? Yes. V equal to F1 lambda 1, which is 247 Hertz times 1.2 meter, that is 296.4 meter per second is the speed of transverse waves on that string. If the linear mass density is given, what should be the tension when the wire is in tune? If this wire is in tune, what is the tension on that wire? Well, how do we find the tension? We know the wave speed. We know the linear mass density. Isn't it possible to use these to find the tension? Because you know V equal to square root of T over mu. There we are. Can you solve for T from here? T will be V squared multiplied by mu. We got the value of mu, we got the value of V, therefore the tension must be, this is the mu value, this is the velocity, and you square it. That gives me 87.9 Newton is the tension of that string when that string is in tune. So I hope you now have a fair idea what is the meaning of tuning a musical instrument and what is the relation between the fundamental frequency and the length of the wire and so on. Now later on we will spend a few more minutes on talking about musical instruments, then we will talk about all this one more time. Well, I'm going to close this lesson here. Please go back and do the homework. Alright, we are now nearing the almost the end of Unit 1. There are a couple more lessons left. I will see you for the next lesson a little later.